do another hypothesis test for the difference between two population proportions. So we have here a professor asked 245 students if they were satisfied with their grade on a test. Of the 95 students that read the textbook, 81 said they were satisfied with their grade. Of the 150 students that did not read the textbook, 93 said they were satisfied with their grade. At a 5% significance level, test the claim that the proportion of students that read the textbook and were satisfied with their grade is different from the proportion of students that did not read the textbook and were satisfied with their grade. So we have the two populations, the students that read the textbook and the students that did not read the textbook. And amongst the students that read and the students that did not read, we have the successes being counted as those who were satisfied with their grade. So in both cases, we're counting a success as being someone who was satisfied with their grade. We get two proportions. P1 is the proportion of those that read the textbook that were satisfied with their grade, and P2 is the proportion of those that did not read the textbook that were satisfied with their grade. And we're concerned with the parameter P1 minus P2, the difference in those proportions. And what we're going to use a sample, or two samples actually, one sample from each proportion, and we're going to use the samples that are spoken of here from the professor to try to estimate about the population of all students that read the book versus all students that do not. So the sample is the 245 students that this professor surveyed. And from those two samples, or from that sample, we have 95 that read the book. So N1, the sample size for those that read the book, is 95. And of those 95, 81 were satisfied with their grade. And then for those that did not read the book, the sample size was 150. And of those 150, 93 were satisfied with their grade. We can use that to calculate a sample statistic. And the sample statistic would be 81 over 95 minus 93 over 150. And that sample statistic, D null, or the null difference, is 0.2326. That's the difference between this sample proportion P hat 1 and this sample proportion P hat 2. So we have the null distribution, and because of the fact that we're looking to see if P1 minus P2 is equal to 0, meaning there is no difference between the two proportions, and P1 minus P2 not equal 0 is the alternative hypothesis, meaning that there is some difference. So the null hypothesis is that there's no difference in the two proportions, and the alternative hypothesis is that there is a difference, that the difference is not equal to 0. Because we have the null hypothesis, the D null, or the hypothesized difference, being 0, 0 is going to be at the center of my sampling distribution, which is the null distribution. So at the center of this specific sampling distribution, which we call the null distribution, is the null value of 0. So we have a sample though, a sample statistic, and the sample statistic is the difference between those two P hats, P hat 1 and P hat 2, which is 0.2326. We want to know where that sample statistic falls in the sampling distribution that is the null distribution. We want to know where it falls. So we need to know something about the center. Well, we know the center is 0. We need to know about the spread of this null distribution. So it turns out that this test statistic, this sample statistic, has a test statistic that is normally distributed with a mean of 0, because that's what the null value is, and a variance that's equal to this red bit here, the pooled proportion, the pooled sample proportion times its complement over N1, plus the pooled sample proportion times its complement over N2. That would be the variance of this normal distribution, as long as the success failure condition is met. So if you meet the success failure condition, then you have a normally distributed population here, or a normally distributed sampling distribution with mean 0 and this as its variance. So we'll be able to calculate a test statistic from this sample statistic 0.2326. And we can calculate this by first we're going to find the pooled sample proportion, and that's 0.7102. We plug it in here to find out what our actual variance is. And it turns out the variance is 0.0035 when you do the calculations. So I have a normal distribution with a mean of 0 and a variance of 0.0035. And there I can calculate the test statistic by taking the sample statistic, which is D null hat, or the difference between P1 hat and P2 hat. Then I'm subtracting from that D null, which is the null value from the null hypothesis, which says that it's equal to 0. And I'm dividing that by the square root of the variance, which is the standard deviation. And for a sampling distribution, it's actually called a standard error. So I'm dividing by the square root of the variance here to get the standard error. And 0.2326 is the sample statistic. I subtract 0, I get just 2.2326, and I divide by the square root of the variance there, which this square root is the standard error, and I get 0.39 or 3.91. So 3.91 is my test statistic. Once you have the test statistic, 3.91, you can use it to calculate the p-value. Now, because the alternative hypothesis is that the difference is not equal to 0, I can then use I can then find the p-value by finding the area to the right of the test statistic, or to the right of the sample statistic if you're looking at the sampling distribution. But because it's a two-tailed test, I'm not just looking at that area to the right for a positive test statistic. I'm also looking at the area on the left, because I don't care if it's a lot greater in significance or a lot smaller, significantly smaller. I just care that it's different. So I'm not looking necessarily for something to be greater than the null value or something to be less than the null value. I'm just looking for either one. So I'm just looking for it to be different than the null value. So I need twice the area to the right of this positive test statistic. If the test statistic were a negative z-score, I'd look for twice the area to the left of that test statistic. But because it's positive, I'm looking for twice the area to the right to find the p-value. So I'm going to use Python, and here's how I'm going to use it. I'm going to import scipy.stats as stats, and then I'm going to use the stats.norm.cdf with 3.91, but in order to find the area to the right, remember the CDF only gives you the area to the left, I have to do 1 minus. So 1 minus that function is, or that method is going to give me the area to the right of 3.91, and I have to multiply it by 2. So I double it, I multiply it by 2, and this is the value I get. So I have that my p-value is equal to this. That's a very small p-value. What this is saying is, if the null distribution and thus the null hypothesis is true, if this is the correct distribution, then the sample that I've actually observed has this as its probability under the null distribution. So either I'm experiencing a miracle here, either we've had a miracle happen with this sample, or this null distribution is incorrect. So, because this p-value is less than the stated cutoff point for significance, which was 0.05, anything that was less than or equal to 5% of a probability we said was going to be significant, then we have to reject this null hypothesis, because this is really, really significant. This is a miraculous sample, like I said, and we reject the null distribution because we don't believe that this miracle occurred. We believe rather that we had the wrong assumption about what the actual null value was. And we don't believe that P1 minus P2 is equal to 0. We believe that it's different from 0. So we're rejecting the null hypothesis in favor of the alternative.